All right, so Tuesday morning, just a few days left, and we're in the process of solving for beam deflections using this, what I call or refer to as the double integration method. We did one example yesterday. We're going to go through and work another example today. And then we have one other method to look at called superposition. And then that'll be the end of the course. Just remind you, mention this, but see written down here, our last test 4, final exam, whatever you want to call it, 1 week from today. So next Tuesday, August the 4th. And also note, be aware, the time is different. Again, the exam schedule time is 8 to 11, but this is just going to be an hour and a half test. So 8 a.m. to 9:30 a.m. Next Tuesday. And we'll cover everything that we've done since the last test. So it's what we did in Chapter 11 with beam design. And then in Chapter 8, we did pressure vessels and combined axial and bending. And what we're doing in Chapter 12 with beam deflection. So that's what the test next Tuesday covers. And we'll talk some more about that in the next couple of days. Specifically, Thursday, our last day of class, that's basically all we're going to do is talk about the test, go over any questions you have over those, over that material. All right. So that's where we're at. Anybody have a question about anything before we embark on this second example? Right, nothing showing up in the chat. So I'm assuming that means no questions at this moment. So let's try to do another one of these. This example, we're going to try to find the equation the elastic curve. Again, this is the terminology he uses. All right, so we're trying to find an equation y. It's going to be a function of x that basically gives what the deformed shape of this beam is, and we're going to try to find the equation for the entire beam. So all the way down the beam, we want an equation that gives us the deflection or displacement for this. And our particular beam here, we have it's a simply supported beam with a pin support at end A, roller support here at end B. And we've got some concentrated force P that's located someplace along this beam. It's not in the center. So this would be A, this would be B. Those dimensions not necessarily equal. And, the entire length of the beam, L. And I think I mentioned this yesterday, but this is typically what most of the problems in this section are going to look like in terms of, you're not going to have specific numbers. Most of these problems are going to be like this in terms of P and L and A and B. We're not going to have, 100 pounds or 10 kilonewtons and 10 feet long. And again, I know students preferred problems with numbers in them, but it really shouldn't matter. I mean, you work it the same way, whether you got a number for L or P or just use variable. But anyway, just giving you a heads up, that's what most of the problems in this section tend to look like. And, innocent enough looking problem. In fact, Actually, in fact, if you look at the one we did yesterday, we had this triangular shaped distributed load acting on the beam. You would look at it and think, well, that would be more complicated than this, because this is just a simply supported beam with one force somewhere acting along the beam. But you're going to see, sometimes looks can be deceiving. Again, might look relatively short and easy and innocent. Sometimes turns out to be a little bit more work involved than you might think. So anyway, this is the problem, and we want to try to find an equation for y that gives us the displacement all the way down the beam. So before we get started too much further, I know I've got support reactions. Again, for this pin support, we're going to have reactions AY and capable of having AX here, but again, by observation, I know AX is 0, so I'm just going to leave it off. And we got a vertical reaction here at the roller support, and we'll call BY. Now, if you think back, or remember back to when we started chapter 6, we saw that our shear force and moment equations will change wherever the loading changes. So this particular beam with this loading is going to require us to cut this thing twice. We're going to have to cut it somewhere between the left end A before we get to that applied load P, because we're going to get one set of equations for V and M for that section of the beam, and then we will have to cut it again somewhere past where the loading changes. We're going to get a different set of equations for V and M on that section of the beam. It's going to require us to cut it twice. Now, I'm thinking ahead, and when I cut this, I'm going to cut it and look at the left side. So in doing so, I will definitely need to know what AY is, but I don't need to know what BY is. So I'm going to save myself a little bit of work, and I'm just going to calculate what AY is. And so the easiest way to do that would be to sum the moments about B. So if we sum the moments about B, it's got to be 0. If counterclockwise is positive, I'm going to have this force P times that distance B is a positive moment. AY acting up causes a clockwise moment, so that would be a negative moment. AY times L, and that's got to equal 0. And if we solve for AY, I get PB over L. And I know I mentioned this yesterday. When you're solving these problems, you need to solve for the support reactions in terms of, again, these variables that are given. You should never have like AY in your answer, right? So always solve for those support reactions. So as I said a second ago, right, we're going to have to cut this thing somewhere. Again, we're going to come out here some arbitrary distance X and cut it somewhere before we get to our applied load P. And I'm going to draw a new free body diagram here. And keep in mind the results that we're about to compute are only valid for this part of the beam, for X values between 0 and A. So we come out here, again, some arbitrary distance X and cut it. And this is end A. We just found AY was PB over L. And we're going to have this internal shear force and this internal bending moment. They're going to be acting on that cross section. And again, we're cutting it before we get to P. So that's it. If I cut it here and I look at everything to the left, this is all I got. And so it's relatively, again, simple, straightforward. This is what we're trying to solve for. Also remind you, assume this is in the positive direction. Otherwise, again, our answer is going to be a negative of what we're intending to calculate. And this is the positive direction, what we define to be positive. So I discussed some of the moments about this point where I cut it, and we're going to call it P. And as I mentioned yesterday, motivation for that is if we sum the moments here, we don't have to solve for our shear force Dx. So sum the moments about that point P. And I've got the moment, the internal moment that I'm trying to calculate. And AY over here is causing a clockwise moment, so that'd be negative PB over L times that distance x equals 0. And we solve for our moment. So our moment here, we move this to the other side, becomes positive. Yeah, it's PBX over L. So that's going to be the moment along this beam everywhere. Again, from the left end when x is 0 all the way up to where x is equal to a. So that's what we're going to integrate, right? So remember, we had our differential equation. Said the second derivative with respect to x is equal to 1 over EI times that moment equation. So this is where we're going to plug in that moment equation. 1 over EI times PdX over L. And that's what we solve by integrating. And again, we have to integrate twice, hence the name double integration. So we integrate once, we'll get dy dx, or if you prefer theta of x. Mentioned this yesterday, we're always assuming E and I are constant with respect to x. So no tapered beams where the cross-section changes, no material changes. So 1 over EI, yeah, we can just pull that constant out. And we integrate. And we integrate with respect to x. So we'd have PB x squared over 2L plus a constant. Call it C1. And also, just some notation here. You're going to see in a minute, when we have to cut it again, just past that loading, we're going to get a different set of equations. So just to differentiate between the two, I want to call this theta 1. And now we integrate again. So we integrate dy dx. We get just y of x. And again, I'm going to denote this as y1. We get 1 over EI. Integrating with respect to x, we're going to get x cubed over 3 times 2 would be 6L in the denominator. So PB x cubed over 6L. We've got a constant. We integrate that with respect to x. We just get the constant times x plus a second constant of integration. Right? So these are my equation for the slope or the angle and the deflection, the displacement. So now we would love to be able to solve for these two constants of integration, C1 and C2. All right, so this is where we would hopefully use our boundary conditions and be able to determine what these constants are. Right, so if you look at our boundary conditions we have, just abbreviating boundary conditions as BC. Go back and look at our beam. It's simply supported. It's got a pin support here and a roller here. So when we apply this force, this beam's going to bend, going to deform. But what we know is at this end, the deflection is 0. Right? It can't move up or down because we've got a pin support there. So I know the displacement y when x is 0 is equal to 0. Also know the displacement over at the right end is also 0. Right? It's resting on that roller support. It can't move down. So my displacement when x is equal to L is also 0. Right? I know y is 0 at this end when x is 0. And I know y is 0 at that end when x is L. Question whether we'll use any other or just the y of x. Now, sometimes you'll be asked to find what the slope is. And if you're asked to find what the slope is, then you would use this equation for theta to calculate the slope. This particular problem, it just asks us to find the equation of elastic curve, which is the y of x. But quite often, especially if you got a cantilever beam like we had yesterday, I think one we did yesterday was cantilever. Now you might want to know what the slope is at the end of that free end, right? So in which case you would use this equation for the slope or theta. But here's where our quandary comes in. We can only use one of these boundary conditions for these equations. Remember, these equations are only valid for this first part of the beam. These equations are useless out here at this end when x is equal to L. So we can't use the fact that the displacement is 0 at the end of the beam for this equation. Right? We can only use this first one, and that one we can use. So again, this I'm going to take 0 and plug it in here for y, plug 0 in for x, and we should be able to solve for C2. Right? So I have 0, right? I'm plugging 0 in here for the y, and it's 1 over EI. And I'm plugging 0 in wherever there's an x. So this is going to be 0 plus C1 times 0 plus C2. And we can cancel the 1 over EI, and we get C2 is 0. So I know at this point C2 here is 0. And this is where I see students, again, all the time make mistake. They'll come and use this equation. They'll plug x equals L in there and solve for C1. And it's wrong because you can't use this one, right? So we just make note and understand why we can't use this boundary condition. Like, again, these equations are only valid for those x values. It's not valid when x is equal to L. So that's, at this point, that's all we can do. We can find C2, and then we have to move on. Any question about that idea or why we cannot use the fact when x is equal to L, y is 0? All right, so then, well, let's continue, move on. And right, we're going to have to come out here somewhere past where that load changes, right? Some arbitrary distance x past the load change and do the same thing. And we'll get a different set of equations because we're going to get a different moment equation. So I will draw a new free body diagram. Again, this is end A. We've got our support reaction PB over L. And we've got this applied force P here. This location or this distance A. And we're cutting this at some arbitrary position X. And we want to, again, find what this internal bending moment is for this section of the beam between, again, where P was applied and the end of the beam. And just like up here, these equations we got were only valid for this part of the beam, for these x values. Again, what we're about to get here is only going to be valid for this part of the beam. Right? This moment equation we get is only going to be good for this section between where the force is applied and at the end of the beam at B. So these x values are the only thing that will be applicable to these equations. So like we did up there, we're going to sum the moments about this point where we cut it. And we got a P in here already, so maybe we'll call this D, something different, so I don't have two P's in here. So sum the moments about that point where you cut it, and solve for that moment acting on that cross section. So if we sum the moments about that point D, set it equal to 0, what we're going to get is my moment. This P, we need to know what that distance is away from D where we cut it. Well, if this distance is x, and this distance is a, this distance is going to be x minus a. That's causing a positive moment. So P times x minus a. And then minus our ay times x. So minus PB over L times x. I think that's everything. We got our moment. Again, by summing the moments about this point, we eliminate the shear force V. We got P times x minus a. So I think that's it. Now it's got to be equal to 0. Now, here's where I'm going to do something that you don't have to do. If you were solving this problem, first time you were going through this, you probably wouldn't do this. But experience, I've solved a bunch of these problems, and somewhere you can either do some simplifying down the road, or we can do a little simplifying now that might save us a little more simplifying later on. Again, you don't have to do this, but just an observation here. In this equation, I'm going to have A's, and I got a B, and I got L. You know, if we can eliminate one of those now, it might, we might have one less term to deal with later down the road. So just an observation here. I know B here is, since I got A's and L's, if I just substitute in the fact that B is equal to L minus A, if we take the total length L and we subtract A, that's what B's got to be equal to. This distance B is just L minus A. If we plug that in, I got, and I'll just leave it like this for right now. Again, all of that would be times x. And I'm going to skip just a little bit of algebra here, but again, you multiply this out and you combine some terms. You move them to the other side, the signs are going to change. So I'm skipping a little bit of algebra. But I wound up with minus PA times x over L plus PA. Again, if you don't make that substitution, that's fine. You'll just have another term down here. It's got a B in it. So you'll wind up with 3 terms instead of 2. But that's okay. At the end, you would, as long as you do it, bring everything along with you, it'll be fine. That is okay if you leave that B in there. What you can't leave in there is AY, right? That, if you leave AY there, that's a no-no. But if you got A's, B's, and L's, that's okay. All right, so that's our moment. So now we're going to do exactly the same thing we did up here. We're going to plug that in our differential equation. Right? I know the second derivative is equal to 1 over EI times that moment. So minus PAX over L plus PA. And we integrate twice. So we're going to take this and integrate. So now we're going to get dy dx or theta. And here, again, I'm differentiate between this equation for theta and this one is calling this theta 1, this theta 2. 1 over EI. And we integrate with respect to x. So we have minus PA. Here we're going to get x squared over 2 over times L. PA times x plus a constant. And again, to avoid confusion, I've seen it done two ways. I'm going to call it C3. But it's also fairly common. I've seen these problems solved where they'll call the constants up here C1 and C2, and down here they'll call them D1 and D2. If you want to do that, that's fine. Or if you want to call these C3 and C4, just make sure you differentiate. We're talking about different constants here than the constants up there. And now we integrate again, and we get our displacement function. Again, I'll denote y2, 1 over EI. Integrating with respect to x. X cubed over 3, so we get x cubed over 6L. PA x squared over 2 plus C3 times x plus C4. Right, we get a new different constant of integration. And let me mention, because another fairly common thing I see students do that I really don't understand why students do this, but I've seen students do it enough. I think it is worth mentioning. We're integrating with respect to x. But I see students all the time do problems like this. They'll be integrating with respect to L or A or B. X is your variable, always. So you're always integrating with respect to x. All right, well, we went from having one unknown constant, right? We didn't know what C1 was up here. Now I got two more. Well, now here's where we can use this boundary condition, right? Because remember, these equations we got here are valid for this part of the beam, right? For x equals L, I can apply this boundary condition to these equations. I cannot apply this one, the fact that the displacement is 0 when x is 0. I can't use that down here, right? So just make note here, we can't use this boundary condition. Again, these equations are only valid for x values that are bigger than a, right? They're not valid when x is 0. Right, but we can use this one, right? And so that's what I'm going to do down here. I think I got room. I'll stick it at the bottom. Right, I know when x is L, y is 0. So I'm going to plug 0 in here for y. And now I'm plugging L in here for x. So I get minus PA. I'm going to have L cubed over L, so I'm going to wind up with L squared. Right? And that L is going to cancel. We'll just have 6 in the denominator. Here I got PA. Plugging L in here for x, I get L squared over 2. And then plus C3 times L plus C4. Well, the 1 over EI cancels again, and then what we wind up with, again, these two terms are like terms. I could actually combine those. All right, I got a minus PAL squared over 6 and a PAL squared over 2. You get a common denominator, it comes out to be a positive PAL squared over 3 plus C3 times L plus C4. I'm going to call this equation 1. Because notice I got two unknowns in this equation. I can't solve for C3 or C4 at this point. And so now here's where, when we started out this nice innocent looking problem, we're running into a situation where I've cut it twice. I got my two moment equations. I've integrated those, and I got my slope and displacement for the first section, but I got an unknown constant, C1. Down here, same thing, integrated, apply my boundary conditions. I still have two unknown constants of integration. So we still got three unknown constants of integration. And at this point, we only have one equation. We can't solve for three unknowns with one equation. So here's where we must employ what I mentioned yesterday. The book refers to as continuity conditions. Right? That's where we're going to get our other two equations from. And in just a second, I'm obviously got to get a new sheet of paper. But basically what the continuity condition says is, these equations here are good for, this part of the beam. The equations I got here are good for this part of the beam. But right there where they meet, when x is actually equal to a, these equations have to give me the same values as these down here do, right? Because I have a nice, smooth, continuous beam here. So right here, at this point, where x is equal to a, this equation's got to give me the same value as that one. And that's what the continuity conditions are, right? So I can turn the page. All right. So I might be able to keep that around. We'll have to come back to that in a second. So the continuity conditions. Again, maybe I'll draw a new picture here. Right, we're applying this force P here at x equals a. It's going to cause this beam to deform. Again, displacement in each end is 0. But right here, right where x is equal to a, I got to get the same. Now, the equations we had on the previous page were theta 1 of x and y1 of x. Right? These were the equations for this part of the beam. Right? For x values up to a. But then we had the second set of equations. They were for this part of the beam. Right? Those equations apply to this part of the beam. But right here where they meet, they got to give me the same values. So the continuity condition here is that, again, theta 1, when x is equal to a, it's got to equal theta 2 when x is equal to a. Right here, x equals a. And so I go back to those two equations. I plug x equals a into each one, and I set them equal to each other. All right, so here's where, again, I'm going to, looking back at my previous sheet. All right, so we're looking back at this sheet. We're going to take, say, this equation here and this equation. All right, this is the equation for theta 1. This is the equation for theta 2. We're going to plug x equals a into this one and set it equal to this one when we plug x equals a into it. All right, so everybody with me as to what we're doing? All right, so again, I got to move this out of the way. And so for theta 1, I got 1 over EI. And I had PBX squared. So I'm going to plug in A in for X. So now I have A squared over 2L plus C1. And that's got to equal to, when I plug X equals A into theta 2 equation. So I'm going to get 1 over EI. And I had a minus PAX squared. But if I'm plugging A in for X, I'm going to have A times A squared. That'll be A cubed. PA cubed over 2L. Plus I had PAX. So I plug A in for X, I'm going to get PA squared. And then plus C3. All right, is everybody following with me? That's the... What I did was just plug X equal to A in those two equations and set them equal to each other. Well, we can cancel the 1 over EI. And I've got this equation, PBA squared over 2L plus C1 got to equal minus PA cubed over 2L plus PA squared plus C3. Call this equation 2. All right. Remember what I call equation 1, we had two unknowns in there with C3 and C4. Here I got this equation, my two unknowns are C1 and C3. We got one more equation we need. And that we get that from setting the y values equal to each other at x equals a. So we're going to take y1 when x equals a, set it equal to y2 when x equals a. And again, what we're doing now, if we go back, look at this previous sheet, we're taking this equation here, y1, and we're going to plug x equals a into that equation. And we're going to set it equal to this equation, plugging a in here for x. Because those two displacements got to be equal to each other when x equals a. Right? So that's what we're doing. And write this down. So we're going to get 1 over EI. Again, plugging a in for x into that y equation, I'm going to get, it's PBX cubed, so I'm going to get PBA cubed over 6L plus C1 times x, so that'd be C1 times a. That's equal to 1 over EI. Plugging a in for x to the y2, I get minus PA times a cubed. That would be a to the 4th over 6L. And I had a PAX squared, so that'd be PA cubed over 2 plus C3 times x, so C3 times a, and plus C4. Cancel the 1 over EI's, and so now we wind up with this big ugly mess. Minus PA to the 4th over 6L plus PA cubed over 2 plus C3 times A plus C4. And now we've got 3 equations, 3 unknowns. And I'm going to spare you the pain and agony of going through this algebra. I actually went through this, but if you take our three equations, just remind you we had equation 1 from the previous page, right, that involved our unknown constants of integration. So we take this equation, and then these two equations, and we got three equations, three unknowns. And again, I'm going to skip all the fun algebra. And this is what I got. I got C1 comes out to be minus PBL over 6 plus PB cubed over 6L. I got C3 was minus PAL over 3 minus PA cubed over 6L. And then finally I got C4 was PA cubed over 6. And ease some of your, I'm sure some of your anxiety at this point, thinking, oh my goodness, if next Tuesday we have a problem like this where I got to take those three equations and solve for three unknowns, don't worry, I would not give you a problem where you would have to go through that messy algebra. Again, you're going to have an hour and a half to do the test. I don't want you to spend 15, 20 minutes just going through trying to solve, three equations and three unknowns with that messy of algebra. So on the test, you would not encounter one where the algebra was this messy. Okay? But it's possible in some of those suggested problems in the book, you might run into something, gets messy like this. And remember, we started out with a really, really simple problem, right? We had a simple beam, one force acting on it. And now we're down to solving this. I won't use the term I started to say, but it gets ugly, right? The algebra does. But now we're done, right? All we got to basically do now is go back and plug those constants of integration in. So again, we were asked to find, what the equation of the elastic curve was for this entire beam. So we've got two equations. We've got an equation for x values between 0 and a. All right, that's where we call this y1 of x. So we go back and look at our previous page. Here's my equation. We just got to plug in what we just found C1 was. And so we plug that in for C, where we got C1, and I get 1 over EI. We had PBX cubed over 6L. And then C1, that's where we're going to plug in C1, minus PBL over 6 plus PB cubed over 6L. And that was times X. So we're taking C1, plugging in here. And that's it. That's half of our answer. Right. If you graph that, what it would give you is this curved line. That's what the beam looks like from x equals 0 to x equals a. Now, we got a different equation for this section of the beam. So for x values between a and L, right, that's where we had the second equation. Y2 of x, we call that. 1 over EI. So now, if I go back to that first page again, we're taking this equation, excuse me, and we're going to substitute in what we found C3 and C4 were, and then that'll be our answer. So going back, we had minus PAX cubed over 6L plus PAX squared over 2. And then we had C3 times X. So here we're plugging in C3, which was minus PAL over 3 minus PA cubed over 6L. That's where we plugged in C3. That was times X. And then we had plus C4, was PA cubed over 6. And we plugged in C4. That is the equation of the elastic curve for this part of the beam. So again, who would have thought we started out with something simple looking like this, and we wind up with these equations for our displacement.
Are we going to have the option to solve between this method and superposition method?
You're going to need to know how to do both. So now you'll probably have one problem where I'll specify solve using double integration, and you'll have one problem where I'll specify solve using superposition. All right, but any other questions about how we wound up with this answer? Again, on the test, there's problems that I can find and pick that the algebra doesn't get anywhere near this messy. The process is the same, but you don't necessarily get bogged down in all the algebra. All right, so just a couple of minutes. Again, we're not going to have time. I don't want to start talking about superposition today. So just a couple of minutes, one little observation before we, again, we'll start superposition tomorrow. It's tempting when you look at a problem like this. A lot of people would assume that you're going to get your maximum deflection where you apply that force P. And I know this because I've seen a lot of students try to solve a problem like this. And it makes solving it a whole lot easier because, well, if your maximum deflection is at x equals a, then you can set theta or the slope equal to 0 there. Only problem is the maximum deflection does not occur at that point. Right, and so that's what I wanted to take just a couple minutes and maybe mention is that the Y max is going to occur one of two places. It occurs where the slope dy dx or theta, however you want to refer to it, is 0, or at the endpoints. Right? This would occur where, like if you had like the one we just worked, you've got a simply supported beam. Right? It's going to deform. Right? That's where you get the slope equals 0. That's where you get Y max. Right? The endpoints would be like if you had a cantilever beam. Right? Say this thing deforms, it bends down like this, like the one we worked yesterday. Right? That's where you would get Y max, is at the end. Right? So if you have a problem that asks you to find Y max, if it's one like this, set theta equal to 0 and solve for x. Right? So that's what you would do. Right? So you would set theta x equal to 0 Solve for x. That will tell you where y max occurs, right? So that'll give you the x value where y max is. Obviously, if you got it one like this, it's going to be at the end. So just plug in x equals whatever the end, whatever the length of that beam is. So if you go back to that problem we just worked, we had theta 1 was, we'll go back to, I got to go back and look somewhere over here. It was 1 over EI times PBX squared over 2L plus C1. So C1 was minus PBL over 6 plus PB cubed over 6L. I think I'm looking at the right thing. So if we set that equal to 0, so if we have 0 equals 1 over EI times this stuff, right? The 1 over EI is cancel. And so we have this is equal to 0. So PBX squared over 2L minus PBL over 6 plus PB cubed over 6L equals 0. And we're trying to solve for x. So we're going to move this stuff to the other side. And then I'm going to multiply by 2L and divide by PB. This will be a positive PBL over 6 minus PB cubed over 6L. And when you multiply this out, you notice the PB and the PB cancels. So you're going to have 2 over 6, that'll be L squared over 3. Here the P's cancel, one of the B's cancel, so you have B squared over 6. 2 over 6 is 3. I think that's right. If I'm doing my algebra right. So y max is going to be at x equals the square root of this. No, this is not at x equals a. Right? But that's how you would find. If you wanted to, that previous problem we just worked, if it asked you to find, where y max occurs and what y max is, this is where it occurs, and then you would take that x value and plug it into your y equation, and that would give you y max. But it's not going to be where that force is applied unless that force was right in the center. Now, if it was right in the center, then you could use symmetry, and it would be, right? If you had this, you had P, and this was L over 2, and this was L over 2. Yeah, y max is going to occur right there halfway. But that only works if you got symmetry. Obviously, the one we did, it wasn't in the center. And you see the maximum displacement is not where the force is applied, and it's not at the center either. All right? So, out of time, anything else you want to ask about double integration? All right, tomorrow we'll do superposition. I think you'll find those problems a lot shorter, maybe easier than these. Definitely shorter. I don't know. Easier is the best term, but it'll be shorter. As always, if you got questions, stick around in a couple of minutes. Let me get everything stopped recording, and then I'll answer questions if you have them.